Hello and welcome to Mechanical Y. Today we are doing part 2 of a 3-part series of microlessons on the mathematical equations used to accurately represent conic sections. Now conic sections are created when you take a set of cones like this. Now these cones are equal to each other and extend infinitely into either direction, and they are joined at the vertex. A conic section is created when you take a cutting plane and you slice through these cones at a particular angle. Today, we're specifically looking at a conic section known as a parabola. Now this parabola is created when you take a cutting plane that cuts through one of these cones perfectly parallel to the side of the cone. And you get a shape that looks something like this. So let's take a look at the mathematical equations that can be used to define this shape accurately. Okay, so here I have a typical shape for a parabola. Now what I've done is I've placed this parabola on an xy coordinate system such that the origin is at the tip of the parabola with the x direction going this way, bisecting the parabola in half, and then the y direction moving upward this way, tangent to the tip of the parabola. So the first thing we're going to do is we're going to define a very important point. This point is known as the focus. And we're going to call it F. So we have a focus named F. Other conics actually may have more than one focus. They actually have two. In the case of a parabola, we only have one. Now focus is defined in a very particular way, such that if I have a line coming in parallel to X at any point along the y-axis, when it strikes the parabola, it can reflect, and it reflects at an angle relative to the tangent of that particular point. It'll always reflect directly towards the focus. Now this doesn't matter where I draw this line from and where it intersects. It'll always come in, and as long as it comes in parallel to the x-axis, it'll always strike the parabola and find itself going towards the focus. Now this is a very important property for the use of a parabola. Parabolas are used in focusing dishes such as mirrors, reflectors, headlight reflectors, and radar dishes. And this is an important property because you can have a beam of something coming in this direction, such as light or a radio wave, and no matter where it hits this parabola, it'll always reflect toward a central point. And in this case, this could be either a point where you're trying to focus light or electromagnetic radiation, such as in a radar dish, or you'll have a source here like a light bulb and you're trying to get all the light to go parallel. So this is an easy way to define where the focus is, but we need to be a little more precise. We can define the location of the focus given the edge of the parabola, and we're going to call this parameter A. Now for lack of a better term, we are going to refer to A as a semi-major axis. Now semi-major axis is a term used for all other conics. However, in the case of a parabola, it doesn't really make sense because there is no major axis. But we're going to use this terminology anyway for the sake of consistency and clarity. So now that we've defined the location of A, the location of the focus relative to the edge of the parabola, let's look at another common term that we find in conics, and that is the semi-minor axis. And we usually call that B. Now as it turns out, when we deal with parabolas, there is no semi-minor axis. So we don't have to worry about that term at all. So now we can actually define the location of any point around this parabola, which I'm going to call x, y. We can define the location of that point around this parabola using only the parameter A. And here we get the fundamental equation for a parabola, where the distance y squared is equal to 4 times the parameter A times the location x squared. So now, given this coordinate system, xy, and any location of any point along the parabola, xy, and given only the parameter a, I can write this equation. And it is true for all time. Next, let's look at a point called the linear eccentricity. And let's call that line C. Now typically for other conics, C is defined as a line that goes from the origin of your xy axis, which is typically the center of the conic, to your focus F. The way we've defined it here, the linear eccentricity is actually just equal to A. So it really has no additional meaning, but let's go ahead and define it just for the sake of consistency, and we're going to use it a little bit later. Now we are going to define something new. Here is a line. Now this line is known as a directrix. Now directrix has a special property. Let's say we take a line that starts at the focus and goes to the edge of the parabola. And let's call the length of this line d1. Now from this point where that line intersects the parabola, we draw a line that is perpendicular to the directrix and intersects that point. And let's call that distance d2. We find that the ratio of d1 over d2 is equal to a constant. And that doesn't matter where I draw this line from. So I could draw it up here, so long as I draw a second line, d2, that's perpendicular to that directrix. This relationship always holds. And it defines a property that we call the eccentricity. Known as E. And we say that this constant is that value. Now we're going to define another term, and it's called the semi-lattice rectum. We start at the focus, and we move parallel to the y direction. And we keep moving until we hit the edge of the parabola. Now the length of this line is given as L. So we have the semi-lattice rectum given as L, with the lattice rectum being defined as a line that goes from one edge of the parabola to the other, that is parallel to the y-axis or perpendicular to the x-axis, depending on how you look at it, and passes through the focus. And finally, we define one final parameter, and that is the location of this directrix relative to the focus. And we call this the parameter P, known as the focal parameter. So now we have several parameters about this parabola that help define its shape. But we need to be able to know how to calculate these values. Just naming them doesn't really help. And we're going to try to put this all in terms of this value A, because this is usually given or known. And if it's not given or known, it's typically very easy to find out. So first, let's start with the parameter. Let's start with two parameters that we know are true for all conics. We know that the eccentricity of a conic can be defined as the parameter C over A, or it can be defined as the parameter L over P. So it's the linear eccentricity over the semi-minor major axis, or the eccentricity can be defined as the semi-lattice rectum over the focal parameter. Now these are two equations that we know are true for all conics. And we're going to use these equations to figure out what the rest of these parameters are. So first, we have that C is equal to A. And this is something that we defined earlier as being true. So now what we could do is that we could take this equation and plug it into this general equation for eccentricity. And we simply get that the eccentricity is equal to 1. Because if c is equal to a, then this just ends up being a over a, which is equal to 1. And this is a defining feature of a parabola. A parabola can be defined as a conic whose eccentricity is exactly equal to 1. So now let's try to define equations for the semi-lattice rectum and the focal parameter. Well, we know that this point up here, where the semi-lattice rectum touches the parabola, is distance a in the x direction and distance L in the y direction. So this defines that point. So now we can take this and plug it into our original equation for the shape of a parabola. So we get that L squared, which is the distance in the y direction, is equal to 4 times a times the distance in the x direction, which is also equal to a. So we get that L squared is equal to 4a squared. Solving for L, we actually find that L is equal to 2 times a. Now we could take this and plug it into this equation that is true for all conics. And we find that the focal parameter P is also equal to 2a. So now we have our equations. We have 2 equations that are true for all conics. We do not need to derive these. And then we have 5 equations that precisely define the shape of this conic given very important parameters. Thank you for watching. I hope you found this interesting. If you did, please like and share this video. And please subscribe to stay up to date on future micro lessons.